In order to investigate conservation of momentum, let's take a look at a collision involving two different objects. Let's say that we have object A, which is moving initially to the right. We'll call that V sub A. And let's just say we have object B that's initially moving to the left, V sub B. What will happen is these two will end up colliding with each other. So A and B are going to interact with each other. Let's say after the collision, A is going to be moving to the left and B is going to be moving to the right. In order to understand what's happening with the momentum, it's probably best to take a look at what's happening during the collision, during the moment that A and B are impacting each other. We know that the time that A is hitting B is some sort of a time interval. I'll call that delta TA. And we know that the time interval that B is hitting A is also a time interval, delta TB. We know that these two time intervals are going to be equal. In other words, we know that the time that A is in contact with B would be equal to the time that B is in contact with A. It wouldn't make a lot of sense to have A pushing B for a longer period of time than B is pushing A when they're both in contact with each other for the same duration of time. If we look at our free body diagrams, on A, we know that we have a force of B back on A. And if we look at B, we know we have a force of A back on B. Because of Newton's third law, we know that the magnitude of the force of B on A is equal to the magnitude of the force of A on B. Well, since we know the time interval where both objects are going to be in contact with each other, and we know the two forces that are applied on each, if we look at the impulse, which is force times the change in time, that's going to equal to the change in momentum. So essentially, if we look at the force on A times the time of A, that's going to equal the change in momentum of A. If we look at the force on B and the time interval on B, that's going to equal the change in the momentum of B. Well, we know that the force of B on A and the force of A on B are the same, which means that the force of A, I'll just say, is the force of A on B. And the time of A is just going to be delta TA. Well, we know for B that I can still use the force of A on B because we know that the force of B on A is equal to the force of A on B in magnitude. And then for the time, we know that the times are the same as well, which means that for delta TB, that's the same as delta TA, which means that these two are equal to each other, which means that the change in momentum of A is equal to the change in momentum of B. So basically, the derivation of our conservation of momentum comes from Newton's third law. Because we know that the magnitude of the force on A and B and the force of B on A are the same, and we know the time interval when they're in contact will be the same, therefore we know that the impulse would be the same, which means the change in momentum for each of them will be the same. And I really should say it's the magnitude of the change in momentum. What ends up happening then is I can say that the magnitude of the change in momentum of A minus the magnitude of the change in momentum of B is going to equal 0. Thus, momentum is conserved. Whatever momentum A loses will be gained by B. Just like we have in Newton's third law, the forces are equal but opposite. The change in momentum of each is going to be equal but opposite, which means that the total amount of momentum in the same remains the same throughout the collision. That's the conservation of momentum.